Hey everyone, welcome to another lecture video, this time chapter 5, and we are going to be going over molecules and compounds. Now I want to start off just by showing you guys a couple of pictures and just talking a little bit about how elements are different from molecules. So here on the left, we see table sugar. Let's go right here. Table sugar. Now ordinary table sugar is called sucrose. Sucrose is a disaccharide made up of glucose and fructose, but we're not going to go into that here. Now, a sucrose molecule that's shown here contains carbon, it contains hydrogen, contains oxygen, and the properties of sucrose are very different from those of carbon, shown here in the form of graphite. So, while they both contain carbon, well, actually, there's more here. So, graphite, hydrogen, oxygen, all of those. I don't have hydrogen and oxygen shown. O2 would be just the air. Hydrogen wouldn't necessarily be in the air. But sucrose with those atoms is different than collections of those atoms individually. Let me give you a better example. Elemental sodium, right? Elemental sodium is extremely reactive. It dulls almost instantly upon exposure to air. Metals are usually shiny, but this thing reacts. If you put it in water, it explodes. Not explodes like TNT, but gives off so much heat in the reaction that the gases around it expand rapidly, and it gets very hot and it's very violent. Elemental chlorine. Elemental chlorine is a yellow gas with a pungent odor. It's a highly reactive and poisonous substance. Now you put these together, and we have sodium chloride. Now sodium chloride, otherwise known as table salt, is quite different, right? We use it. In fact, we need this. Our bodies absolutely need salt, sodium chloride. We use those ions, the sodium ion and the chlorine ion, for various functions in our bodies. Not to mention that they make food taste super good. And then in the old days, if you killed a big animal, you either had to eat the whole thing right then, or you had to worry about spoiling, your meat spoiling, because there was no refrigeration, of course, unless you lived in the snow and you could just pack your meat into the snow. So you had to figure out a way to make your meat last, and drying it was one of those ways, and salt was used for that. Now, many natural substances are compounds. Some of the everyday substances that we encounter in everyday life are elements, but but most are not elements. Like oxygen, for example, is an element, and we do encounter oxygen in the elemental form. But most of what we encounter are going to be compounds. Now, free atoms in nature are rare, and a compound is different from a mixture of elements. Remember, we did talk about pure substances versus mixtures. A compound isn't the same thing as a mixture, though it does have different atoms combined. The difference is, in a compound, we have fixed proportions, fixed or definite proportions, versus in a mixture, we can have variable proportions. So here is two examples. These two balloons both contain only oxygen and hydrogen atoms. Now the difference is, in this balloon, there are oxygen atoms as O2 and there are hydrogen atoms as H2, but there's no real rhyme or reason to how many there needs to be in relation to those other atoms. Let me explain. I count 1, 2, 3, 4, 5 oxygen molecules. 5 times 2 is 10. So there's 10 O's. Let's count how many heliums there are, or hydrogens. 2, 4, 6, 8, 10, 12. So there are 10 oxygens to every 12 hydrogens. 10 to 12. That would be the ratio of O to H. Now, in a mixture, every time we look at this ratio, it could be different. Every single time we look, it could be different. Sometimes there might be more oxygens. Sometimes there might be more hydrogens. Sometimes they might be exactly equal. The number of hydrogens might equal the number of oxygens. That's possible with these molecules since they come in twos, right? They're all just pairs. But let's compare that to a compound. So this balloon only has water in it. I don't want to count every single water molecule here. I guess I can. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. I counted between 20 and 21. I don't want to count it again. I am counting the ones that I can barely see also, but I think I might have counted this guy twice. You can check that. Let's just go with 20 and say that there's 20 so I can illustrate my point. Or actually, we'll do both, 20 or 21. So if there was 20 oxygens, 20 waters, what this implies is that there are 20 oxygens to every water molecule has 2 hydrogens. So this would be just double, right? 20 water molecules would be 40 hydrogens. So the ratio of O to H would be 1 over 2. There would be 1 O to every H. Now let's say I was wrong. There isn't 20. There's actually 21. Well, that would have been 21 O's, or 21 water molecules, which would have had 21 O's, and then it would have had 42 H's, right? Because an extra water molecule comes with 2 extra H's. So this ratio of O to H would still be 1 over 2. 21 is half of 42, just like 20 was half of 40. So no matter how big this balloon was, or whether this water came from the ocean or from a cloud, the amount of water in it, if there's only water in it, would indicate that if we looked at the ratio, that this was a compound. And that's what we would see. We would see that the ratio of O to H in a compound is always the same, whereas in a mixture it's different. It varies and it can depend. So, okay. Let's talk about the law of constant composition. It arises from this observation that we just made, that water molecules always have the same ratio of atoms. So Joseph Proust in the late 18th century formally stated the idea that elements combine in fixed proportions to form compounds. And he stated this as the law of constant composition. All samples of a given compound have the same proportions of their constituent elements. So if we were to take, let's say, for example, 18 grams of water, and we were to break it down, we would get 16 grams of O and 2 grams of H. The ratio of their masses of O to H, and we always arrange this to get numbers bigger than 1, because you might say, why did we put O over H? Well, if we put H over O, 2 divided by 16 is a small number, less than 1. So they always arrange these to get whole numbers, okay? Smaller number on bottom. So the ratio is 8, and that would be true for water obtained from anywhere. So if you have a sample that you know has hydrogen and oxygen in it, but you aren't sure what it is, say that you don't know if it could be water, it might be hydrogen peroxide. Hydrogen peroxide has the formula H2O2, right? So if it just has H's and O's in it, you don't really know what it is. If you were to decompose it, see the ratio of the masses, and it matches the ratio of the masses known for water, then it's probably water. Okay. I'll give you another example. If we were to take 17 grams of ammonia is NH3, and we were to get just the nitrogen and hydrogen out of that, we'd get 14 grams of nitrogen, we'd get 3 grams of hydrogen, and we would see the ratio is 4.7. Or the way that we say it is that there are 4.7 grams of nitrogen to every 1 gram of hydrogen. 2. We say that. 4.7 to 1. Okay, now even though atoms combine in whole number ratios, their masses don't have to be whole numbers, okay? What we're looking at right here is their weights, how heavy they are, their mass, how much space they take up. We're not looking at their number. That is indicated by the formula. There's 1 nitrogen to every 3 hydrogens, or there's 2 hydrogens to every 1 oxygen. So yeah, their masses though don't follow any kind of rule like that. Now, I could give you, just to give you an idea of what kind of question I could ask you. I could say, here are two samples, sample 1 and sample 2. Sample 1 has, 17.3 grams of nitrogen to every 4.5 grams of hydrogen. And sample 2 has 27.6 grams of nitrogen to every 11.3 grams of hydrogen. Do these samples, prove the law of constant composition, or do they follow the law of constant composition, or do they not? Might they be different samples? And you would calculate the mass ratio for both of them and see if they're the same. If they're the same, then it's the same substance. If they're not the same, then they're different substances. So, okay, that's the law of constant composition. Now let's talk a little bit about how we kind of show formulas. So by convention, whenever there's a single atom, we don't show a subscript of 1, meaning that we're not going to come in here where the oxygen is and put a little 1 because there's one O. We just it implies that there's a 1 there. I mean, you can see the O. That means there's at least 1, right? If there's more than 1, then we put a subscript. So that's why you'll see these little 2's there. So the symbol for hydrogen is shown, the symbol for oxygen is shown, and then the subscripts indicating how many of each there are. So chemical formulas, it's common to include, what I was going to say is we follow some rules. We tend to follow some rules. We put certain elements in front. We always list metals before nonmetals. Let's see, some common chemical formulas include things like NaCl for table salt, a 1-to-1 ratio of atoms there, carbon dioxide, CO2, you can see there, two oxygens to 1 carbon, table sugar, C12H22O11. This gives us a 12 to 22 to 11 ratio of atoms there. And so the subscripts in the chemical formulas, they represent the relative numbers of each type of atom in that compound. Now, if you change a subscript, it makes a huge difference, right? CO and CO with a 2 under the O is a completely different compound. Carbon monoxide, as we would call CO, is an air pollutant with adverse health effects. It can actually outcompete oxygen for your hemoglobin, so if there's carbon monoxide around, you basically suffocate. Carbon dioxide, not as deadly. Carbon dioxide we breathe out, so I mean our bodies are already tuned to getting rid of it. Relatively harmless. It's a product of combustion and human metabolism, and we breathe small amounts of it in all the time with no harmful effects. The harmful effect that we get from holding our breath is actually the lack of oxygen. And carbon dioxide doesn't outcompete oxygen. So as soon as we take a breath, oxygen fills our lungs again. In the presence of carbon monoxide, our body is like, hey, I'm going to go get this carbon monoxide molecule because I like it better than oxygen. So even if oxygen's around, you're going to choke on the carbon monoxide. Okay. On that happy note, let's continue. So we list elements in order, as I mentioned, from metal to non-metal. Now, when we go down a column, the more metal-like ones are normally lower on the list. And so, for example, if we were going to write a compound between nitrogen and oxygen, we have a few. We would write NO2 as opposed to O2N. The N would go first because on the periodic table, if you remember, our metals are on that side and our non-metals are on this side. And nitrogen is right here and oxygen is right here. So nitrogen's closer to the metals in terms of it being more on this side. So it would go first. Now if you have trouble, there's a list. You're not going to have to worry about this too much. Right underneath oxygen on the table periodic table elements is sulfur, and metals as well are lower on the list than upper on the list, right? Because this is the upper corner, that's the non-metals. So that means even down here, these are all metals. So sulfur would go before oxygen. We would write SO2 as opposed to O2S. Okay, let's talk a little bit about polyatomic ions. So some chemical formula contain groups of atoms that act as a unit. And when several groups of the same kind are present, their formula is usually set off using some parentheses. So we call these polyatomic ions. And so in order to determine the total number of each type of atom in a compound like this, you actually have to do a little bit of multiplying with the outside subscript. So let's take a look at magnesium nitrate and kind of expand on this one. So here's magnesium nitrate. I know that because I know how to name things and you haven't learned that yet, but we're going to get to that in this chapter. Okay, so first you see here that there is the symbol for magnesium. So the magnesium symbol shown off to the side. Then in parentheses, we see that there's this NO3 group. And NO3 minus is the polyatomic ion. Now you guys are used to monoatomic ions like Cl minus or Br minus, or even, I guess, what would we do, like Na plus. These are fine. You may remember the list that I showed you that does have some of these type of, wait, O2 minus? Sorry, I drew that wrong. It's O2 minus, right? So these are monoatomic ions. Now polyatomic just means that there's multiple atoms together and that they're an ion, so they have a charge. Most of them are negative. There's one that's positive, NH4 plus. Now, in this instance, we see that because magnesium, if you remember, magnesium is actually in column 2 of the periodic table, that makes magnesium have a 2 plus charge. So in order to pair up a ion with magnesium to cancel that charge out, we're going to need 2 of these NO3s because an NO3 only has 1 minus charge on it. But if we were to bring in 2 of these NO3s, and they both had a minus charge, then together that would be 2 minuses, and that cancels out. So that's what we see here. So again, if we wanted, let's count how many atoms there are in each of these. So 1 magnesium, we can see that there's no letters, no numbers under it, so it's implied that there's 1. We see here that there's a 2 outside the parentheses. So that means there's 2 sets of whatever's in the parentheses. Within the parentheses, there's 1 N. But because we have 2 of those whole groups, there's 2 N's. How many O's are there? Well, within the parentheses, we see that there are 3 O's. But we have 2 of these groups, so there are 6 O's. Now, why is this important? We're going to need to know how much this weighs. We're going to need the molar mass of this eventually. To get that, we're going to add up the masses of all of the elements inside it. If you are unable to look at this formula and know that it actually contains 9 atoms and not just 3 atoms, then you won't get the same formula that we will, that I will, or that the answer key will, right? Okay. Let's talk about types of formulas. So there are empirical formulas. And an empirical formula gives the relative number of atoms. So it would, I'll put another kind of row up here. Let me give you an H2O2 and a sugar, C6H12O6. Actually, I shouldn't have done that. Let's put those up here. H2O2, C6H12O6, and I'm going to call this empirical. Okay, the empirical formula is the simplest whole number ratio. So for methane, which we're looking at in all of these pictures here, this is methane, CH4 is as simple as we get. 1 carbon, 4 hydrogens. So the empirical formula would be exactly the same as the molecular formula. But for these two up here, that would not be the case. We could actually go simpler. For the case of H2O2, we could say that it's HO, one H to every O. Two H's to every two O's is the same thing as one H to every O. What about for C6H12O6? CH2O. For every carbon, there's an oxygen, and for every carbon, there's two hydrogens. And that's still true. So empirical formula is the simplest ratio. Now, then there's the molecular formula. This gives the actual number of atoms. And then there's the structural formula. This shows with lines to show chemical bonds how the atoms are connected. Then there's the ball and stick models that represent the atoms as balls and chemical bonds as sticks. The balls are color-coded. Hydrogen's white, carbon's black, nitrogen blue, oxygen red, fluorine's kind of a greenish color, phosphorus purple, and so on. And then there's the space-filling model. These these atoms fill the spaces around each other and more closely represent our best idea for how a molecule might appear if we could scale it to be visible. And so, images like this make the connection between the world around us and the world of atoms and molecules. So the macroscopic world that we see and the atomic molecular world, the one that's particles that compose matter, and sort of the symbolic way that chemists represent the atomic and the molecular world is with all of these together. So macroscopic, but the symbolic sort of view of the molecular world. So we're going to use a lot of these models. We like space filling, and we're going to use a lot of ball and stick to represent how geometries look in 3D space. Now, we'll start off a little more simply by just trying to get a wrap on empirical formulas and molecular formulas, and then by chapter 10, we're going to be doing Lewis structures and drawing these on our own. Okay. So, pure substances can either be elements, which can be atomic or molecular, and then they can be compounds, which might be molecular or ionic. So let's first talk about atomic elements and molecular elements. So we're going to go down this branch first and talk about these guys. So atomic elements are those that exist in nature with single atoms as their basic units. Molecular elements, and by the way, most elements fall into the atomic element category. Molecular elements do not exist in nature with single atoms. Instead, they exist as diatomic molecules, so two atoms of the same element bonded together. And so here you can see just a basic unit of mercury, single atoms, and then the basic unit of chlorine. Chlorine is one of those diatomic molecules. And so what we call it is a molecular element, because it's a molecule. Molecules are more than one atom by definition. Compounds are also molecules, but not all molecules are compounds, right? This molecular element is not a compound, because a compound has more than one type of atom. This only has one kind of atom. So atomic element, molecular element. Now here's a list of the molecular elements. There's not very many. That's them. That's all of them. It's easier to memorize this list than to try to figure out from some other way, or to memorize all of the ones that are atomic. Okay, so compounds can then also be molecular, or they can be ionic. Now, molecular compounds are those formed from two or more nonmetals, where the ionics are formed by two or more metals. I'm sorry, that's a lie. One metal and one nonmetal. So molecular compounds, which I'm showing you here, and ionic. So ionic compounds contain one or more cations paired with one or more anions. And these usually always happen with metals and nonmetals. Metals we know like to form cations, and nonmetals we know like to form anions, or negatively charged ions, and cations positively charged ions. So let's talk a little bit about writing formulas for ionic compounds. So when a metal has the tendency to lose electrons, combines with a nonmetal, which has the tendency to gain electrons, one or more electron transfers, and we end up with an ionic bond. An ionic bond is not a sharing of electrons, it is a relationship that results from the opposite charges attracting each other. Okay. Now, when you guys are writing formulas for these, I left a couple of rules for you. So write the symbol. So we can do one of these. So let's write the formula for I don't know, beryllium fluoride. So beryllium fluoride. All right. So write the symbol for the metal and its charge, followed by the symbol for the nonmetal and its charge. So beryllium is in column 2. So beryllium 2+. All right, symbol for the nonmetal and its charge. Fluorine. It's a halogen. It's in group 7, -1. Okay, make the magnitude of the charge on each ion, without the sign, become the subscript for the other ion. What does that mean? It means make the 1 that's above fluorine be the 1 under beryllium, and the 2 above beryllium be the number under the fluorine. If that sounds funny, it's meant to look like this. So by doing this, we are going to basically create the formula. Another way of thinking about it, right? What cancels out 2 pluses? Well, it'd have to be 2 minuses. Does fluorine have 2 minuses? No. So what if we did this? Brought in another fluorine. Do these 2 minuses cancel out the beryllium? If yes, then we just write down how many of each atom we have. 1 beryllium, 2 fluorines. It's the same as if we took the 2 and brought it under the fluorine, and the 1 and brought it under the beryllium. Okay. If possible, reduce the subscripts to give a ratio with the smallest number. So if we had this written down for some reason, Be2F2, we would just reduce this to just be BeF. That's what that means. And then we want to make sure that the charges actually cancel. This is why it's super important that you actually start with the right charges. So when in doubt, check, look it up. Don't just guess. All right, so here we have just 2 examples, formulas for aluminum and oxygen and magnesium and oxygen. Now these are ionic compounds, cations and anions together. Now, I mentioned that we do have to write formulas for compounds with polyatomic ions. And so you got to recognize polyatomic ions in a chemical formula. You got to become familiar with these. You don't have to know the names of all of these, but you should know the names of at least those guys. Those are stars. Yeah. So I would know those names. Now, of course, you don't have to know all of these, but you're going to have this table to be able to reference. All right. Let me show you how we would write a couple formulas here. So let's just take the only positively charged guy and write a couple formulas with that. So let's pair that with a Cl minus and also with an O2 minus. So for the Cl minus, we're simply going to write NH4 Cl, right? If we were crisscrossing and dropping down the numbers, they're both 1s. So that's how we end up with that. Now here we can see the O is a 2 minus and the NH4 is a +1. So we're going to need 2 of these NH4s. NH4. Now the way that you show 2 of them is you put parentheses around them, like that. Now why is this important? Well, let me show you in another example. let's take hydroxide, a minus, and pair that with a couple positive charges. Let's pair the first one with Na and the second one with aluminum. Okay, so we would write Na, we would write OH, we'd start with their charges, and then we'd crisscross. They're both ones, so this would become NaOH. For the second one, we're going to go, aluminum 3 plus, OH minus. Now, we're going to bring a 3 down here, and we're going to bring a 1 over here. Now, watch what happens if I just do that. Now, how many O's are in this whole molecule? Just one, right? There's 3 H's, but there's only 1 O. Is there supposed to be only 1 O, or are we supposed to have 3 of these hydroxides, meaning 3 O's, 3 H's? So parentheses make sure that you get the right number of elements. You can see it's easy to leave off those parentheses and easy to lose a couple O's in the process if we don't include parentheses. When in doubt, put a parenthesis, but you don't always need them. Okay. So let's talk about naming. So chemists have developed systematic ways to name compounds. So if you learn the naming rules, you can examine a compound's formula and determine its name, and vice versa. So many compounds have common names, like water has, water's a common name. The systematic name would be dihydrogen monoxide. But since water is a familiar compound, everyone says water and not its common name or systematic name. Common names can be learned only through familiarity. There's no system. You just have to learn them. Now, as far as the system goes, let's start by naming ionic compounds. And the first step to naming an ionic compound is identifying one. So you got to remember, when you see a metal and a non-metal together, you can assume it's an ionic compound. That means you need to pay attention and figure out where your metals and your non-metals are, and be actively looking at what type of element is in your compound. Okay, so the first rule that we're going to look at is the difference between the types of ionic compounds. So for ionic compounds, there's the type where the metal forms only one type of ion. These were from the metals from our main group. And then there's those that form more than one type of ion. These were from our transition group. All right, so once you have figured out what type of metal you have, the first type is going to be called type 1, the second type 2, and let me show you some of the common charges. Now these are invariant charges. Even some transition elements only have one charge that they tend to form, and so we can memorize those. But for the most part, you've got +1s, +2s, +3s, and then a couple of variants in the middle. Now, these are going to be our type 1 ionic compounds. So if I have calcium and sulfur, and I know sulfur is a nonmetal, calcium is a metal, and I want to write these as a ionic compound, I already know calcium is 2 plus. I already know sulfur is 2 minus because I remember how the trend on these is, and then I would write CaS. On the other hand, if I'm looking at this formula, CaS, and I want to name it, I have to know that calcium doesn't have more than one charge. I need to know that calcium is in that 2 plus column. That way, when I'm naming it, I name it properly. When we name these, we just say the name of the metal. Oops, we haven't shown you the rules yet. The name of the metal, and then we're going to say the non-metal with an IDE ending, but we'll get there. So I wanted to show you the other metals. So these are these are the variant metals. And these are their names. So when we say chromium in a compound, we're going to say chromium 2 or chromium 3. We have to say those words. Now this is not all of the metals. This is only a small list. This only shows the two most common ions for each of these metals as well. They can form more than just these two ions. But when we talk about iron, we tend to only see iron 2 and iron 3, or copper, copper 1 and copper 2, or lead, lead 2 and lead 4. So that's what these are. Now these older names do have some relevance when we're naming acids, because these us and ic endings often will tell us whether or not we have more or less charge. So you'll notice all the OUS's are paired with the lesser charge of their ions, and the ic endings are paired with the higher charges of those. Okay, naming ionic compounds. If they're binary, then that just means that they only have two elements, and that makes it easy for us. So for binary compounds, we're just going to say the name of the metal, and then the name of the anion or the nonmetal with an IDE ending. And here are some common IDE endings. So here's fluorine, an anion. We would say fluoride. Here's oxygen, oxide. So let's name let's do an example. Let's name sodium chloride, right? Or that's too easy. Let's name this one. I'll write it down and you guys will name it. So we'll go okay. So sorry. So this has a metal and a nonmetal. The name of the metal, we would look it up. Potassium. Name of the nonmetal, bromine. So we'll give it a ide ending, potassium bromide. Let's do another one. How about so here we have Na2O. That doesn't change anything. We don't care if there's a 3 here or 11. It doesn't matter. We're going to call this sodium. We're just going to say the name of the metal, and then we're going to say oxygen as oxide. And this is true also if we had something like BeCl2. This is just name of the metal, beryllium. I can't spell. Beryllium, and then chlorine, chloride. We don't say chlorides with an S, or like 2 chlorides or dichloride, nothing like that. We don't care about those little subscripts. Those subscripts are important because they tell us the charges, and that's something we need to know. But they don't influence the name as far as the anion goes. Now, when do they influence the name? Well, they influence the name with the type 2s. So let's look at the type 2s. So for our type 2s, we have, because these can have multiple charges, the charge has to be specified in the name. And we usually specify the charge in parentheses in Roman numerals. So for example, copper, if we go back to this previous table, you saw that copper had a couple of different charges. Sorry, that's not copper. 1 and copper 2. So let's use that in the example. So let's take copper and pair it with O like this. All right. So we need to figure out what the name of these two compounds are. We're going to be using these rules down here. So the name of the metal, then the charge of the cation, then the base name. So at the moment, both of these are copper. And both of them have an oxygen, so they're both copper oxide. But you see that can't be right, or at least that can't be the whole story, because how could they both be called copper oxide and have different formulas? So we need to figure out what the charge is so that we can call the proper one copper 1 oxide and the other one copper 2 oxide. Now you might look at it and go, oh, I know copper 2 oxide. It's this one, because there's a 2. Incorrect. Now why is that incorrect? Well, that's not copper 2 plus, is it?
You're saying, why is that not copper 2 plus? It's got a 2. Does that 2 tell you the charge, or is that 2 how many coppers there are? So we've got to back up a second. What is the charge on oxygen? Charge on oxygen in this ion is 2 minus. So then what, if this is balanced, meaning opposite charges are canceled, what has to be the charge on the other copper, right on the other atom? Well, in the top case, the copper has to be 2 plus to cancel out a 2 minus. But in the bottom case, there's 2 coppers. If both of those coppers were 2 plus, that would be 4 plus. That wouldn't balance the oxygen. So these coppers have to be 1 plus. And because there's 2 of them, that's why it is canceled out. So the top there is copper 2, and the bottom is copper 1, even though copper 2 or copper 1 has a 2 in it. So this is why it becomes important to know your charges, on top of the fact that we have to pair them up properly when we write them. Now we have to learn how to name them properly. I'll give you another example. So you can already see here that there are 2 types of iron. Both of these can't be called iron chloride. So which one of these is iron 2 chloride and which one is iron 3 chloride? Iron 2 chloride. How do I know? Because I know the charge on chlorine. The charge on chlorine is -1. There's 2 of them. So there's a -2 negative. So this iron has to be a +2. Over here, this 3 tells me that there's -3 charge total over here. And so this has to be +3. So that's how you figure out which metal is which. Now, we're not done. Ionic compounds also have polyatomic ions that we have to worry about. Now, some ionic compounds contain polyatomic ions, and so we need to know how to name these. These are a little easier to name. We just say the name of the polyatomic ion. So, for example, let's say that I want to name this thing. So first, I need to recognize that there's a polyatomic ion in here. There's NO3. I have to recognize that as a polyatomic ion. So study that list of ions I showed you. Next, what are the rules? Well, you say the name of the metal, you say the name of the anion with an IDE ending. Well, we're not going to do the IDE ending stuff with this. We're just going to say the name of the polyatomic. So this would be sodium, because that's the metal. Sodium doesn't have any other, there's not sodium 1, sodium 2. If there was, we would put the parenthesis. And then we say the name of the polyatomic. In this case, it's the NO3, so it's nitrate. Notice that the ATE ending has the more oxygens, and the ITE ending has less oxygens. That does not mean that 8 means 3 and that ite means 2. That is the case sometimes. 8 means 3, ite means 2, right? 8 and ite, 3 and 2, 8 and ite, 3 and 2. That just means more and less. Take a look. 8 in sulfate is 4. Ite is 3. So don't memorize it as they mean a certain number. It just means 8 is more, ite is less. Now, if there's even less than ite, we add a hypo in front. So here you can see for these ions that have 4 different numbers of oxygens, these only have 2. But if you have 4, then in addition to ite and 8, we can go hypochlorite and hyper, we don't say the hype part, we just say perchlorate. So hypo is even less and hyper is even more. Again, the hyper here is not shown, but that's where it comes from. All right, so naming these, again, you just use um, the names. These guys. So again, the ones you want to know: nitrate, nitrite, sulfate, sulfite, and so on. Let's try one more. How about if we did this? NH4 Cl. How would we name this? So we recognize polyatomic, we find it, ammonium is the name, and then chlorine would just get the chloride. Remember? Chloride. What if it wasn't chlorine? What if it was a different polyatomic? What if it was this guy, ClO4 minus? Well, then it would be ammonium perchlorate. You just say the name. So these will be the funnest for you guys to name. Of course, you'll have the internet, which will make this a lot easier for you. Again, I can see if you just Google the name, though. But the idea would be to try. Well, the idea is really I'm not going to ask you a lot of naming questions on the test. I've already written the tests, and there's not a lot of naming questions for that reason. I can't really test you on that virtually. But that's how you would name this. And if you are moving on in this class, and you think you're going to need to know how to name, then you should probably really try to learn those. Okay, we can also do polyatomic ions that have the invariable, the variable metals as well. So, like for example, we could go FeNO3 2 and FeNO3 3, and this would be iron 2 nitrate. This would be iron 3 nitrate. And I would know that because 3 of the minus charges have to balance off 3 positives. 2 of the minus charges, a 2 positive. Okay, notice that they're not always 1 minus. The sulfates are 2 minuses, right? So that's a difference. Phosphate is 3 minus. Okay. These are going to be important to know because we're going to pair these with hydrogens and make acids. And when we name the acids, the way we name them will depend on whether it's the ate or the ite. So that's coming. Okay, I wanted to show this picture because often a lot of the active ingredients in household items like bleach are written as polyatomic ions. So sodium hypochlorite is bleach. Hypochlorite, so ClO, because chlorite is ClO2, hypochlorite is ClO. Sodium bicarbonate, baking soda. Calcium carbonate, active ingredient in Tums. Let's see, and Alka-Seltzers and that kind of stuff. Baking soda, sodium bicarbonate, we use that because it releases carbon dioxide in baking. And then sodium nitrite. Sodium nitrite. It's often a preservative, food additive. Helps preserve food like hot dogs, ham, bologna. It inhibits the growth of bacteria, especially those that cause botulism. So, yeah, useful. Okay, let's talk about naming molecular compounds. So the first step in naming a molecular compound is identifying it as one. These are made of non-metals. So if you see metals, then you've got an ionic compound and you want to name it with the rules for ionic compounds. So how do we name this guy? Well, that's not a real compound anyways, but hey, there's a potassium. So go back, 15 minutes in the video and name that one. How do we name this guy? Well, that's different. These are all nonmetals. NO3, SO2, CO2, right? All of these. Now, we're not going to name anything that has more than two types of atoms in it. That's beyond the scope of this class. So as long as there's two types of atoms, we can do it. So what we're going to do here is make sure first they're all nonmetals. If they're all nonmetals, then we are going to follow these rules. We're going to give a prefix, and then the name, and then a prefix, and then an ending change on that second name, just like we did for the ionics. The prefix come from here and are going to be based on how many of those atoms there are. Right? We can do this. So let's try. Now, a couple of rules. First off, if there is if there's only one atom in the first element, then normally we would not put mono. Okay, we're not going to say mono if we don't, like for this guy right here, let's name it. It's nitrogen. We should say mono nitrogen. We throw that off. We don't say it. So let's just say nitrogen. Now there's 3 oxygens here. So 3 is tri, and then oxygen is oxide. Remember IDE? Nitrogen trioxide. Let's try another one. Sulfur dioxide, because there's 2 O's and di. Carbon dioxide. Let's try this one, a little different. Dihydrogen, 1 sulfur, monosulfide. Dihydrogen monosulfide. Remember H2O? Dihydrogen monoxide. Monoxide. It's too many O's. Smush them together. Diiodide. Too many I's. Diodide. Smush them together. Oh, I'm sorry. The vowel does get dropped in monoxide, but not in dioxide or trioxide. Triiodide. So diiodide, triiodide. Sorry, we would still say that. We wouldn't smush them together. Okay, let's name this last one. Tetra carbon hexa fluorine fluoride. Tetracarbon hexafluoride. Like it? So these are completely different naming than the others. These, we do look at the subscripts. These don't have charges in them. So they're completely different. You don't want to get this compound and name it disodium monoxide. Right? Disodium monoxide. It's not a molecular compound. This is a metal and a nonmetal. So it's not named the same way. Okay, acids. First step in naming an acid is identifying one. How do we know if it's an acid? Well, it has an H on the front. They are binary. HF, HCl, HBr, H2S technically, and H2O. These are acids. Binary in that they only have 2 elements, not necessarily that they only have 2 atoms. But this is almost all of them right here, all the binaries. And then there are oxyacids. Now, oxyacids get named different than binary. Binaries get named one way, oxyacids get named another. Let's list some oxyacids. We've got HNO3 and HNO2. We've got H2SO4 and H2SO3. Why do we have 2 H's on those? Well, remember, the nitrate ion was a -1 and the sulfate was a -2. Hydrogen itself is a +1, so remember it's right there in the column 1. So in order to cancel out the charges, we need to add an extra hydrogen. Phosphate was PO4 3-, so H3PO4 for phosphate or phosphoric acid. So these are oxyacids. They are acids that contain oxygens. Let's go over the naming. So for our binary acids, the naming is actually pretty easy. With binary acids, we just say the word hydro, then we change the name of the nonmetal to have ic. So we'll name the first 3. hydroiodine becomes iodic, and we say acid. We say hydrofluorine becomes fluoric, we say acid. Chlorine, hydrochloric acid. Okay. Let me write one more. HCl3. Okay. So let's talk about how we name oxyacids. Now, oxyacids, let's see, did I? Yeah, okay. Oxyacids get named based on the polyatomic ion that they have in them. So if they are made with the oxyanion that ends in "ite," they take the form of an OUS ending. So let's look at some of those. So the OUS endings come from the ites. Okay. This is nitrite. So this would be nitrous acid. This one right here is sulfite. So it would be sulfurous acid. Okay. Then Ix. The ic endings come from the 8 anions. So this is nitrate. This is sulfate. And again, I know that we know this, the 8s have more oxygens in them, remember? You can think of it as they're 8 because they ate more oxygens or something like that. I don't know. So it would be nitric acid or sulfuric acid. Now I want to show you one more thing here. So this one right here is chlorate. So this would be chloric acid. Now, hydrochloric acid and chloric acid are completely different, right? HCl is hydrochloric acid, but HClO3 is chloric acid. Note the difference. When we say hydrochloric, it means it's binary. It only has 2 elements in it, no oxygens. If we don't say hydro, it implies that there's O's. Chloric acid versus chlorous acid versus hyperchloric acid. What'll look different? Chloric, chlorous, and hyperchloric. Then when I left off was, not hyper, perchloric. Hypochloric is the other one. Hypochloric. One oxygen, 2 oxygens, 3 oxygens, 4 oxygens. Yeah, without the high part on it, just per. So those are acids. Fun, right? So these are some common acids, and they're oxyanions. So nitrous, nitric, sulfurous, sulfuric. You can see how that works there. Carbonic and acetic are others that we use all the time and that we talk about. Again, recognizable hydrogen in front. Acetic comes from the polyatomic ion acetate. And since acetate ends in an 8, you give it the ic ending, acetic. Carbonate as well, carbonic. All right, so this is the flow chart. Basically shows you all of the acids and how to name them. Okay, and here's one more. This one gives you examples of a formula. Kind of shows you how you would go through naming it. Molecular, both nonmetals. Ionic, metal and a nonmetal. If it's got one type of ion. An acid binary. Here's another ionic. This one has more than one type of ion, right? Iron, versus calcium. So main group versus transition. And then oxyacids in ate and ite endings. All right, and then just to kind of wrap this up, let's talk about how acids impact the environment. So acid rain occurs whenever rainwater mixes with pollutants, often nitric oxide, nitrogen dioxide, sulfur dioxide, and so on. These form acids when they mix with water. These come from vehicular emissions. These come from coal-powered electricity generation, burning hydrocarbons in general. And so these make the water acidic. Now, when the water gets acidic, it flows into streams, flows into lakes. Sometimes it raises the pH. I'm sorry, it lowers the pH. It can actually dissolve nutrients, and it can weaken trees. It can also damage buildings. I don't have a picture of gargoyles on big buildings that are made out of stone, but they start to lose their faces right with the acid rain. It just kind of washes it away. All right, last thing that we're going to talk about in this chapter is how to calculate a formula mass. And this is the mass of a molecule or a formula unit. So formula mass is basically, for any compound, we're going to sum up the atomic masses of all of the atoms in the chemical formula. And so if this was carbon dioxide, we would take the number of carbons and get their mass. So this would be number of carbons, 1. The mass of the first carbon, this is 12.011 AMU, right off the periodic table. Number of the second element, there's 2. The mass of oxygen, 15.999 AMU, the periodic table. If we add this up, it comes out to be about 44.01 AMU. I don't have my calculator in front of me, but I do know this one. I've done it too many times. You could do the same thing with water. It's going to be 2 hydrogens and 1 oxygen. This comes out to 18.02. Try doing this yourself. With glucose. Figure out the formula mass of glucose, and then figure out the formula mass of an ionic compound like aluminum nitrate. This will be really good practice. We're going to continue this in Chapter 6 when we look at quantities, chemical quantities. All right, guys, so in this chapter we went over compounds, chemical formulas, chemical nomenclature, formula mass. So how to tell if there was a compound based on their fixed or definite proportions. Chemical formulas, we went over the different types: empirical, molecular, structural, space-filling, ball and stick. Nomenclature, we talked about simple ionic compounds, molecular compounds, and acids that we can examine, that we can identify by examining their formulas. And then we looked at formula mass, which is essentially how to get the sum of the atomic masses for all of those. Hopefully these learning objectives will help you in your studying, and I will see you guys in the next video.